Hi, we are Team MEM3 working with Professor Mazzeo on creating a surfboard propulsion system. Surfing has a steep learning curve as it is a challenging sport with difficult terrain. Thus, our intent is to ease this process for both beginner surfers and provide tools for surfing instructors. We intend to do this by making it easier to catch waves and projecting the surfer into the heart of a wave with the use of an entirely mechanical system based on elastic band energy storage. This will cut down on excess manual paddling and thus make it easier for an instructor and a beginner surfer, making the process far more enjoyable. The constraints that our advisors set for us are that the system should only be operated by a single person, consist of a non-corrosive and durable material, and be able to float above water.
How we managed our project was that we had weekly meetings with our advisor to discuss the physics that we had been working on, the designs that we had been testing. Then we also split our tasks into specific sub-teams so that each sub-team could work on a specific subsystem. And then finally, during experimentation, we would ensure that our entire team was there so that we can maximize efficiency by using our large team. And finally, we had to make sure that we were all communicating because we had a large team. So we'd have weekly meetings over Zoom or in person and have weekly meetings over Discord as well to discuss what was going on.
The final selected design of our project is a slingshot propulsion system, which operates on the same principles of a basic slingshot, in which the elastic potential energy stored in the band is converted into kinetic energy of the surfer, and a trigger mechanism at the rear is used to hold the tension in the bands before it is released to propel the surfer forward. The stability of the system is maintained with an anchoring subsystem along with a large rectangular plate, which will counteract the reaction force of the slingshot. The design objective of providing surfers with a boost to help them catch waves is met through the overall design of the slingshot, which serves the primary purpose of shooting surfers forward and providing them with the necessary kinetic energy to achieve that goal. And we have selected materials for each subsystem that are resistant to the harsh environmental conditions of the ocean, such as waterproofing, corrosion resistance, high strength, etc. And we have included floatable materials so that the system can float and all of the design constraints are met. Also, the system was designed so that it can be operated by a single person. With respect to feasibility, one issue we encountered was that the launch time was too short, which would lead to a very high impulse, which can be dangerous for the surfer. And the solution for this was to extend the length of the frame. With respect to the band material, we needed a material that would store potential energy at greater quantities and would also be waterproof. And so we researched alternative materials for that. A force balance analysis was required, which we went into depth with. And the stability of the system in a fluid environment was a major concern during the slingshot operation. And we resolved this with the addition of an anchoring subsystem along with the drag plate.
After going through all the stuff that was discussed prior, we listed through our different design ideas and we looked at certain metrics such as cost, preference, safety, originality, manufacturability, or feasibility, use, and we created a pew chart based on this so that we can see which was our best idea. And from this, we decided that a slingshot launcher was our best idea and that we would proceed with this. So the slingshot launcher would be broken into four main subsystems, which would be the frame, trigger mechanism, anchor/drag plate, and the band/pulley. And the goal of this project was that when these three subsystems are put together, they are working together to ensure that the surfer goes forward while maintaining a stable system during launch and after the launch. To briefly describe the four main subsystems, the band/pulley is key for slingshot mechanics and energy storage. The flame/flotation is what links all the subsystems, so it provides structural strength as well as buoyancy. The trigger mechanism is useful as it locks and releases the mechanism for loading and tension in the band for the surfer is sent forward. And finally, the anchoring/drag plate provides stability for the system, keeping it fixed in one place and resisting reaction.
Now, to elaborate on the frame, it basically acts as the linkage for all of the other subsystems and provides structural rigidity when the band is loaded with tension. Our design features parallel guide rails along the path of action for the slingshot to provide directional stability while the surfer is launched. This is our CAD model that we developed On the right is our drag plate, which counteracts the pushback force, as previously mentioned, and on the left is the structure of our frame, which is mainly comprised of PVC pipe for optimal rigidity under load. Lastly, these are the individual components that make up our frame, which are 2 joint types, 2 PVC length types, a cap, and a pulley.
The pulley system is where all the energy that is meant to send the board forward is created. It consists of an elastic bands that are connected to ropes that are secured at the back of the frame. There is also a pocket with a marked rope attached to it with an adjustable notch on the rope, which will allow the user to indicate which speed they want to be launched forward at. As the pocket is pulled back via the rope, the energy that is created by the bands will be held in the trigger system. The trigger system is a mechanism that allows for our system to be a single user system. There's a box at the back of the frame which will have a hole where the rope will be fed through, and there will be a spring-loaded lever within the box that will hold the notch on the rope in place until the button is pushed, at which point the energy held in the notch and the rope and the bands will be released and sent into the board, pushing it forward. As the board is pushed forward, there will be a force created that will send the system back. But in order to mitigate that, we have created a drag plate and an anchor. The anchor will help to secure the position of the frame and make sure that it doesn't drift into sea, while the drag plate will help to mitigate the reaction force from the band sending the board into the wave.
And subsystems for the system, and the first subsystem is the band pulley frame, which the input for it is the user pullback of the band, and the output is the elastic potential energy storage for that band. The second subsystem is the trigger release, and the input for that is the elastic potential energy via the pullback of the user, and the output is the kinetic energy of the surfboard. The third subsystem is the anchor and drag plate, and the input for that is the reaction force as a result of tension release, and the output is the reaction force negated from that tension from the drag plate.
The overall force balance was determined based on the free body diagram shown on the slide because it was important to determine what the forces acting were so we can act accordingly. It's visible that in the y direction, the two forces counteract each other, which are the force of buoyancy and the force of weight. But in the x direction, there's a force of the pulley opposing the drag force. The equation for this is also listed, where the force of the pulley is kx because there's elasticity, and the drag force is 1/2 rho x squared times the coefficient of drag times the cross-sectional area. In order for there to be movement, however, this difference in force must equal mx. This means that the force of the pulley must be greater than the force due to drag, and this is the goal of our project.
Iteration of the MATLAB code, and it is used to convert the force balance that we created into an ODE. So this version of the code is very preliminary, and it serves only to lay as the groundwork for the future revisions that we plan on making. So we simplified like constant values, like the spring constant, and we added our own parameters that like made sense. We estimated them. So what we're going to do is with further experimentation, we'll determine the drag coefficient, K constant, and we'll also take into account the angle of attack from the elastic bands and the line of action. So there's definitely further revisions needing to be made.
In our first experiment, we were trying to determine the K constant for our given elastic bands. Material was unknown, so we used F equals Kx to measure the force required to stretch these bands a distance x. We found that on average, it was about anywhere between 33 to 45 K constant. And we used the force, cross-sectional area, original length, and stretch length to determine the elastic modulus of our material, which we found to be made of rubber. For experiment 2, we wanted to determine the feasibility of our project by pulling a surfer across the water to determine the force required to overcome the drag for a given speed. And for our third experiment, we wanted to definitively determine a coefficient of drag to replicate in our ODE, as well as to take into account the angle that the elastic bands take with the line of action of the surfboard to properly determine the amount of force being delivered at a given angle. In our ODE, after changing our variables and determining the position versus time from experimental data, we were able to determine the variable C, representing the drag coefficient multiplied by its area, to match our experimental results. Our ODE has now been updated to reflect a proper drag coefficient as well as the force being delivered based on the angle that the bands have with the surfboard?
Surfing is definitely a tough sport, so our project aims to see that we get an easier process for novice surfers and hopefully instructors. So we developed a design for a mechanical system, which is very similar to a slingshot, that propels a surfer forward using elastic bands. So far, we've created an ODE model and used a force and energy balance equation to simulate theoretical values for the distance and speed of the surfer based on our experimental results that we've obtained. So next semester, we plan to continue testing and refining the design. We want to determine optimal materials. We want to create a final parts list. And then finally, we want to completely construct our design. And we're very excited to do so.